Another thing that we need to be able to understand about accelerated motion is how the graphs of the accelerated motion differ from the graphs that we've been looking at for constant velocity. So just to review constant velocity, we hopefully understand, or we remember from the first unit, that we have position time graphs that are essentially kind of diagonal lines. Sometimes they're horizontal. But you have an example like this. This is a very basic one. This would be an object that's moving forward at a constant velocity. And if I wanted to make the velocity time graph, because the slope of that is positive and constant, it's just quite simply a line at a positive velocity that doesn't change, so a horizontal line. So those are the graphs that we've been used to. Now we have to understand, how do these graphs change when you have acceleration and you actually have an object that is like speeding up or slowing down or changing direction, something along those lines. So for accelerated motion, what we need to do is we need to kind of take a look at what type of graph is created when you have an accelerated object. So if I can slide this down, give me 1 second here. Okay, so here I just have a simulation that's going to allow me to kind of see what's happening with this object. So if we let it run, you'll see in this case that I'm going to give this a constant velocity of 2 meters per second. Again, this is constant velocity motion. So as we said, you see the velocity is a kind of flat boxy graph and the position is a diagonal line. So if I reset this, what we're going to want to figure out now is, if I put some acceleration, which I'll do here in the bottom, how is this position time graph and velocity time graph going to differ? So I'll get rid of these walls up here so that it doesn't bounce off of them. And if you watch the position time and the velocity time graph, you'll hopefully notice there is something very different about the position time graph. It is now a curved line, whereas the velocity time graph is no longer blocky. It looks kind of like the position time graphs we've had previously. So if I zoom in there, you can see that my velocity time graph is no longer blocky. It's now actually a diagonal line. So the big takeaway here, if I kind of accentuate this a little bit more, if I put a larger acceleration, you can really see that you get a curved position time graph and you get a diagonal line on your velocity time graph. So if I go back to what we were looking at here, just to kind of show you examples of that, my position time graph for an accelerated motion is some kind of curved line. Now the way it curves will determine or let you know whether it's speeding up, slowing down, traveling forwards, traveling backwards, but we'll get to that in a second. The velocity time graph is actually now going to be a diagonal line, or will have some diagonal lines on it. So the big takeaway for now is to understand that with an accelerated motion, acceleration produces curved position time graphs. Now that curve can be all sorts of different ways. It can curve up, it can curve down, but just understand the moment you see a curved line on a position time graph, that immediately tells you that that is an accelerating object. The other challenge is that acceleration produces velocity time graphs that have slope. Before, we always had blocky velocity time graphs. So if you really think about it, there was no slope on the velocity time graphs we were looking at. It was a bunch of horizontal lines that we kind of, yes, connected with vertical lines, but there was no slope. There were no slanted diagonal lines on that velocity time graph. So we just need to understand that what we're looking at here in front of us is acceleration. We now have curved position time graphs, and we have velocity time graphs that actually have slopes on them. So that's one of the big differences. Here's the big thing that I want to point out, and this is where, unfortunately, the course gets a little bit more confusing than it might have been in the past. On the left, I have a position time graph and a velocity time graph for an object in which no acceleration is occurring, right? Diagonal line on the position time graph, flat horizontal line on the velocity time graph. And on the right, I have an accelerated position time graph, which is a curved line, and then a velocity time graph with acceleration that has some slope. So if you take a look at all four of these graphs, you might notice something. The position time graph for an object that is not accelerating and the velocity time graph for an object that is accelerating look very similar. But those are two entirely different motions. So we have to start to be extremely careful now, and we always need to look up and see what type of graph we're analyzing, because if you interpret a velocity time graph of acceleration as if it was a position time graph with no acceleration, you'll get the wrong answer, and vice versa. So you're not really going to confuse the accelerated position time graph and the constant velocity time graph, because they just don't look the same. One's a horizontal line and one's a curved line. But the position time graph for no acceleration and the velocity time graph for acceleration are very easily confused for one another. So this is just your first warning. Be very careful. It'll be common in the beginning to kind of misinterpret these as one another, but we just want to start to think about what graph am I given and what information can I get from that. All right, so you guys are going to start to practice sketching these graphs out. We're going to kind of put some of the math off until we get a really good understanding of this. My biggest recommendation is that you get to the point where you can draw out these 6 different categories here: positive constant, negative constant, 0 to positive, 0 to negative, positive to 0, and negative to 0. And you are able to look at these 6 blank spaces and underneath them draw slopes that represent those descriptions. So what I mean by that is, well, for positive constant slope, that's just a line that's going diagonally upwards. So a negative constant slope is just a line that's diagonally going down. And these 4 are what you really have to make sure you understand. 0 to positive means I want to draw a line that's not going to be a diagonal line. It's actually going to be curved, but it's going to curve from 0 slope to a slope that becomes more positive over time. So a 0 slope is horizontal, so I need to go from a line that starts off more or less horizontally and then begins to curve more positively. So that would be a line that looks like that. If you look near the beginning over here, it kind of has like a flat slope and then it becomes more positive over time. Now the one underneath that, 0 to negative, is going to be similar. I need to start with a slope that is kind of horizontal, and then I'm going to become more negative. So it's going to look like this. Now I want to be clear, you're not going from a 0 value to a more negative value. You're going from 0 slope, more or less horizontal, and becoming more negative in terms of slope, not the values. So the reason I highlight that is when we get to these last 2, it can be confusing if you don't understand you're looking at slope. So a positive slope begins going upwards, and then I need to curve this line so that the slope gradually becomes 0, which would be a horizontal line. So from positive to 0 actually looks like that. Now, if you're reading the values, if we assume this was like an x and a y axis, we would be going from a 0 value, the origin, up to a value that becomes more positive because you'd be away from the axis. But that's not what positive to 0 means here. It means we're starting with a positive upward slope, and then the slope over time becomes 0. So please do not confuse positive slope to 0 slope with positive values to 0 values, because those are not the same. So the last one there, a negative slope goes downwards, and then over time I have to become a slope of 0. So that's going to look something like this, where I start going downwards, and then I gradually curve to a 0 slope or horizontal line. It's very important you are able to fill out these 6 different scenarios, because we're going to use those to help us understand how we draw these motion graphs. So if we're going to look at an example here, and this is what you're going to try to move towards today, we're given a written description: a car speeds up, moving forward from rest. So there's a few things that we can get from this sentence, and we're going to use those curved lines over there to try and make the position time graph. So I recommend you consider what's happening with the velocity. So if you read this, it's speeding up from rest, so that's how I know that its velocity started at 0, and then it's moving forward as it speeds up, so its velocity will become more positive. So in parentheses there, we basically are going from 0 velocity to a more positive velocity. Now, those slopes that we've drawn on the side, the slope of a position time graph represents the velocity. So to show 0 velocity becoming more positive, I'm going to need to use this right here, from 0 slope to a more positive slope. So if I just kind of take that right there and I slide that over, you can see here that I'm just drawing that right on the graph. So that's how I wind up getting this line that goes from 0 slope to positive slope. So that is what the position time graph looks like for an object moving forward from rest but speeding up. The velocity time graph, well, how do I show velocity on a velocity time graph? Hopefully you realize I just need to read the graph. So I don't need to draw any kind of curved lines. I simply need to just draw a value at 0, and then later on down the x-axis, some positive value. So I'm going from a 0 velocity, where I'm actually at 0, because this axis gives me velocity, to a more positive velocity. So that's how I have a point at 0 on the y-axis, and some point that's at some positive point further down, and then I just connect those with a line. So over here, I'm going from 0 slope to a positive slope. Over here, I'm going from a 0 velocity to a positive velocity. All right, we'll try another example. A car is now traveling backwards and it's slowing down to a stop. So my recommendation is that you consider what's happening with the velocity. In this case, it's traveling backwards, so it starts with a negative velocity, and then it is slowing down to a stop, so it has to end with 0 velocity. So we know the velocity has to go from a negative value, moving backwards, to 0 at rest. Well, on a position time graph, I'm going to think about the slopes. The slopes need to go from negative to 0, so I'm going to consider my negative to 0 slope over here. It doesn't matter where I draw it on the position time graph as long as I have that shape. So I'm going from a negative slope, not value, that value there is 0, but a negative slope to a 0 slope. To show the velocity, I quite simply just need to go from a negative value, some negative value on the y-axis, to 0. So that's why I'm going to get a line that goes from some negative value on the y-axis up to 0. All right, I'm going to show a couple other examples. Let's see if you guys can figure them out. You can pause the video and then see if you're able to kind of get lined up with my explanation for your response. So I'll wait for a second. You can pause it, try these, and then you can unpause it and listen to the explanation. All right, so in example 1, a car is starting from rest and it speeds up moving backwards. So the velocity begins at 0, and then since it's going backwards, it needs to become more negative. So that means I need to go back and see here. I'm going from 0 to negative. So if I find my 0 to negative, which is right here, that is the shape that I need to add. So 0 to negative, I curve backwards, and then to show 0 to negative velocity, I just start at a 0 value and I move down to a negative value. A car traveling forwards slows to rest and then speeds up backwards. This one is admittedly a little more complicated, but I wanted to show you one that has multiple segments. So this one's a little bit different, but it's moving forwards, so it goes from a positive velocity, slows to rest to 0, and then speeds up backwards. So the velocity is actually go from positive, which is forwards, to 0, which is at rest, to negative, which is moving backwards. So now what I'm going to have to do is I'm going to have to combine some of mine. So if I look at positive to 0, see if I can go back, positive to 0 looks like this. So I have this kind of curve. And then I need to go from 0 to negative, which looks like this, 0 to negative. So what I'm going to do is I'm going to take this piece here, and where I end off, I'm then going to connect this piece and go down. So I'm going to get kind of like an inverted U. I'm going to take this piece, and then from where I left off, I will continue like so. So we'll see if this makes sense, if I draw it out for you. So those are my two pieces. You can see there's a little space there because I'm basically kind of putting them together like a puzzle piece, but you're going to get rid of that, so you're going to draw it in one smooth line. But I just want to show you I'm taking those two different pieces, my positive to 0 and my 0 to negative, and then I'm just connecting them. And then for my velocity, I simply need to go from a positive point down to 0, down to a negative point. So those are my 3 points, from a positive to 0 to negative, and that's how I would kind of analyze or graph a more complicated type of motion.